Hello, welcome to the playlist of videos on essential statistics for data science. I am Hemakumar Kasala, and in this session, I focus on sampling mean distribution and the central limiting theorem. Let's start with a problem to understand the relevance of this topic. A hot dog manufacturer claims that the fat content on an average in the hot dogs made under a certain brand equals 18 grams per hot dog. Random sample of 30 hot dogs were chosen and a sample average for the fat content is calculated and found to be 18.4 grams. Should we accept the manufacturer's claim, or the value 18.4 is large enough to reject the claim? To answer this question, one needs to understand sampling mean distribution, mean of the sampling means, standard deviation of the sampling means, central limiting theorem, Z-curve, and probability measurements. Let's get into the video. Characteristics of population is often measured or estimated using a fixed size sample drawn out of that population. These estimates are called as statistics, to be precise, sample statistics. Statistics can be sample mean, sample median, sample standard deviation, or proportion of individuals in the sample that possess a particular property, like alcohol consumers. These statistics constitute the primary sources of information about the different characteristics of a population. One of the most important statistics is the location estimate, namely the mean. The mean of the above sample, that is the sample mean x bar, is the average value of the sample data. Refer video on data exploration, central tendency, and variability. How does a sample mean relate to the population mean? In other words, how does one go about generalizing this sample mean to the population mean? For a different sample of the same size, the sample mean x bar shall be a different value. Repeating the sampling and calculating the sample mean results in different sample means x bars each time a random sample is drawn. This variability amongst the sample means poses a challenge in generalizing a sample mean x bar to the population mean mu. Hence, it is essential to understand the distribution that the sample means exhibit and the variability within such a distribution. As the sampling is repeated over a large number of times, that is, times tending to infinity, the probability distribution of the sampling mean x bar looks something like this. Hence, the long run behavior, that is, repeated sampling of the sampling mean results in a probability distribution with a certain mean, that is, sampling distribution mean mu of x bar, and a standard deviation sigma of x bar. Note, mu of x bar is the mean of the long run sampling mean distribution. In other words, mean of the sampling means. And standard deviation sigma of x bar is the standard deviation of the sampling mean distribution. In other words, mu of x bar and sigma of x bar are the statistics of sample means, not the sample data. The variability, that is, the standard deviation or variance of the sampling mean distribution varies with the size of the sample n. As varied as the population as n tend towards 1, and as narrow as a single vertical line at mu of x bar as n tend towards the population size n. For a population of a very large size, that is infinite size, or for a finite sized population where the sample size n does not exceed 10% of the population, standard deviation of the sampling mean distribution can be expressed as sigma of x bar equals sigma divided by square root of n, where sigma equals the population standard deviation and n is the sample size. Increasing the sample size n by 4 times, that is 4n, standard deviation of the sampling means sigma of x bar reduces by half. Sigma of x bar in this case equals sigma divided by square root of 4 multiplied by n, which equals sigma divided by the product of square root of 4 and square root of n, which in turn equals half of sigma divided by square root of n. However, unlike the standard deviation or variance, the mean of the sample means mu of x bar remains the same immaterial of the sample size n. And importantly, it equals the population mean mu. Mu of x bar equals mu. Mu of x bar equals mu as n tend towards 1, and mu of x bar equals mu as n tend towards the population size n. Sampling mean distributions for different values of sample size n equals 4 and 16 are shown for an asymmetrically distributed population. For n equals 4, the sampling mean distribution also remains asymmetrical. Whereas for n equals 16, the sampling mean distribution tends to become more normal. With the mean of the sampling means distribution, however, remaining as mu of x bar for all values of n. Sampling mean distribution for different values of sample sizes n equals 4, 16 are shown for a symmetrically or normally distributed population. In case of a normally or symmetrically distributed population, the sampling mean distribution remains symmetrical or normal for any value of n in the range 1 to n. And mean of the sample means distribution remains as mu of x bar for all values of n, like in case of asymmetrically distributed population. Central limiting theorem states that the sampling mean distribution converges towards a normal distribution with larger values of n, even if the population is asymmetrical. However, the sampling mean distribution remains normal distribution for all values of n in the range 1 to n if the population is normally distributed. As per the central limiting theorem, the typical value of n above which the sample mean distribution tends to become normal is fixed based on experimental results at value 30. That is, central limiting theorem applies when n is greater than or equal to 30. Hence, when n is greater than or equal to 30, the resulting sample mean distribution is expected to be normal for any asymmetrically distributed population. For a normally distributed population, the sample mean distribution remains normal for any value of n. How does a normal sample mean distribution with known values of mean of sampling mean distribution means mu of x bar and standard deviation sigma of x bar help in the analysis? Don't forget, mean of the sampling mean distribution mu of x bar equals population mean mu, and standard deviation sigma of x bar equals population standard deviation divided by square root of the sample size, which equals sigma divided by square root of n. First step in the analysis would be to transform the normal sampling mean distribution into a standard normal distribution by subtracting mu of x bar from the sampling mean x bar and dividing the same by sigma of x bar. Termed as z-score, z value equals x bar minus mu of x bar divided by sigma of x bar. Note, the horizontal axis in the sample mean distribution is x bar, while the horizontal axis in the standard normal distribution is the z-score. Value of x bar equals sigma of x bar in the sampling mean distribution translates to z equals 1 in standard normal distribution. Similarly, x bar equals 2 times sigma of x bar translates to z value 2, x bar equals minus sigma of x bar translates to z value minus 1, and x bar equals minus 2 times sigma of x bar translates to z value minus 2. Primary aim of transforming the sample mean distribution into a standard normal distribution and evaluating the z-score is to help calculate the probability values involving x bar. Z-score is quite useful in making important conclusions. Let's get back to the problem posted in the beginning of this video and try and solve using the sample mean distribution and the z-scores. A hot dog manufacturer claims that the fat content on an average in the hot dogs made under a certain brand is 18 grams per hot dog. Let's assume X represents the fat content in each hot dog in grams and exhibit a normal distribution with a population mean value mu equals 18 grams and standard deviation sigma equals 1 gram. Random sample of 36 hot dogs were chosen and a sample mean x bar of the fat content is evaluated and found to be 18.4 grams. The sample mean distribution with sample size equals 36 shall be centered around mu of x bar equals 18 grams, since the population mean is 18 grams. And standard deviation sigma of x bar equals population standard deviation sigma divided by square root of n, which equals 1 divided by square root of 36, which in turn equals 1 divided by 6, and that equals 0.1667. Deriving the standard normal distribution for the means and evaluating the z-score for x equals 18.4, we have z equals x bar minus mu of x bar divided by sigma of x bar, which equals 18.4 minus 18 divided by 0.1667, which in turn equals 2.4. Probability of arriving at a z value as high as 2.4, that is probability of z greater than or equal to 2.4, equals the area under the standard normal distribution curve to the right of 2.4. Probability of z greater than or equal to 2.4 can be evaluated as 0.0081. Note, the above probability value can be derived using the z table that was readily available. Probability of z greater than or equal to 2.4, which equals 0.0081, means that the probability of arriving at a sample mean value of 18.4 is as low as 0.81%. That implies it is very rare. And hence the conclusion of the study can be claim by the manufacturer that the average fat per hot dog equals 18 grams is substantially doubtful. Illustration to derive probability of z greater than or equal to 2.4 using the z table. Pick the value from the table corresponding to the row for 2.4 and column 0.0, since the second digit after the decimal is 0 in 2.4. The value thus picked is 0.4919, which is the area of the z curve between 0 and plus 2.4. Hence, the area of the z curve to the right of 2.4 is 1 minus 2 times 0.4919 divided by 2, which equals 0.0081. For a population distribution that is normally distributed and an asymmetrically distributed population where the sample size chosen is greater than 30, sample mean distribution is normally distributed and central limiting theorem is applicable. Derive the z-score from x bar and evaluate the probabilities associated with x as discussed so far. Whereas, when the sample size is not greater than 30 and the population is asymmetrically distributed, though mu of x bar equals mu and sigma of x bar equals sigma divided by square root of n, Normal distribution, central limiting theorem, and z-scores do not apply. Hence, different models or transformations should be applied in such cases, which are outside the scope of this session. That brings us to the end of the session on sampling distribution, central limiting theorem, and z-scores. Please leave your comments or questions if any, and I shall revert back as soon as possible. Thank you for watching, and see you again with the next session. Bye till then.